Working with inequalities. Lesson objectives: translate verbal expressions into linear inequalities. Graph and write linear inequalities, both single and compound inequalities. Let's begin. Why are inequalities important in statistics? Where they're used in the empirical rule. They are used in percentiles. They are used finding the probability involving the normal distribution. They are used when you write the domain of a linear regression model. They're used in confidence intervals, and they're also used in hypothesis testing. And these are concepts that we will see in future lessons. So when we write inequalities, we look for keywords in the phrases. That will tell us which inequality symbol we should use. Greater than would have keywords like is greater than, is more than, is larger than, exceeds. Greater than or equal to would include is at least, is no less than, is the minimum. Now less than would include is smaller than, has fewer than, or is lower than. And finally, less than or equal to includes is at most, is no more than, is the maximum. So we'll work through a few of these examples. Translate the sentence into an inequality and solve. A number x is at most 20. So our variable is x, and the keyword is at most 20. What this is telling us is the value of x can be any number all the way up until and equal to 20. So this is all numbers all the way up to and including 20. So this would be less than or equal to. So any number that is less than or equal to 20 will make this statement true. To solve it, it's already solved. The variable is all by itself. So when we solve an inequality, we would treat it just like an equation. We use inverse operations to undo it to get the variable isolated, and in this case it's solved. We are done. Let's try another. An unknown number is at least 35. The key word here is at least. If we think about it, at least, you must be at least 16 years old to drive a car. You must be at least 21 to buy alcohol. This is telling us we start at the number and this is greater than. If you are 21 or older, you can buy alcohol. If you are younger than 21, you cannot legally buy alcohol. So for this example, the unknown number is our variable. I'm going to call it x, and we have at least. That is going to be greater than or equal to, and then we have 35. So this is our inequality. X is greater than or equal to 35. This example, a number exceeds 7. The key word is exceeds, and that would tell us greater than. X is greater than 7. Now it's not a greater than or equal to because 7 doesn't exceed 7, but any number larger than 7 would exceed it. Next, a number a that is positive. If we think about a number line, 0 is in the middle. 0 is neither positive nor negative, so we want all numbers to the right of 0. So using our variable a is greater than 0 would mean it's a positive number. Now we want a number y that is negative. Well, that's to the left of 0, so we have y is less than 0. That would give us all the negative numbers. It's not equal to 0 because 0 is not negative. 0 is not positive. It is neutral. Here's our last example for this objective. Twice a number increased by 4 is less than 50. So we want to identify our keywords. Twice a number. Well, the number is going to be our variable. We'll call it x. You can call it n. I'm going to call it x. Twice that number means we multiply it by 2. So twice a number is the same thing as 2x. Increase by, that tells us the operation is addition. Plus 4 is a less than, that is an inequality symbol, less than 50. So we have translated this sentence into an inequality, and now we solve this inequality, and again we solve it just like an equation. We need to get the x by itself, we need to get rid of the 2 and the 4, and if we follow the order of operation in reverse, we get rid of addition or subtraction first. So we need to get rid of the 4. What is it doing to the x? It's adding. We do the opposite and we subtract. So we subtract 4 to both sides, and we are left with 2x is less than 50 minus 4, which is 46. Now to get rid of the 2, we do the inverse of multiplying by 2, which is to divide. So we divide both sides by 2. These cancel, we're left with x, and 46 divided by 2 is 23. So we have x is less than 23. Any number less than 23 will make this inequality true. Now I should mention that if we multiply or divide by a negative number, we flip the inequality symbol. But that's really beyond the scope of this course. So we won't have to really worry about that in this course. The big idea in this lesson is to be able to take a sentence and translate that into a simple inequality. Lesson objective. Graphing the inequality helps us visualize the numbers that will make this inequality true. So in this case we have n is greater than 5. So we have a number line here, and to graph this we just first need to number the number line. I'm going to put 5 right here in the middle, and then I'll count by 1. So this is 4, this is 3, and so forth. And to the right of 5 would be 6, 7, and 8, and so on. This inequality is saying, okay, all numbers that are greater than 5. So that's to the right. All numbers that are larger than 5 will make this inequality true. Now what happens at 5 exactly? Well, this is not an equal to, so we can get as close as we want to 5, but it can't equal 5. And we draw an open circle at 5 to indicate that we can get as close to 5, but it can't equal 5. So just a quick little test. Let's say 7. If I was to check this and put 7 in for n, so we say let n equal 7, then this inequality becomes 7. And is that greater than 5? Is 7 greater than 5? It is. Check. It works. If we picked a number to the left of 5, it would not work. For example, 4. 4 is greater than 5. That's a false statement. Same way as 5. 5 is not greater than 5. Let's do another. Graph the inequality x is less than or equal to a negative 3. Again, we start with the number line. I'm going to put negative 3 here. Then this would be negative 4. This would be negative 5, and so on. And to the right, that would be a negative 2. This is a negative 1, and so on. This time, x can equal a negative 3. So we put a solid circle here to indicate to the reader that it can equal -3. And now we want numbers that are less than -3. Well, that's to the left. So any number in this highlighted area will make this inequality true. Next we have n is greater than -6. I'm going to put -6 here. This would be -7 to the left. This would be -5 to the right. In this case it does not equal, so we have an open circle at 6. And we want numbers greater than -6. Numbers that are to the right. And that is our graph. Again, this is a visual way of seeing the solutions to this inequality. So for example, a 0 is a solution to this inequality. Any positive number is. -5 is. So we have an infinite number of solutions here, and this is a visual way of seeing those solutions. Now let's work backwards. We now are given a graph and we're asked to find what is the inequality. And then we're also asked to find 3 solutions to the inequality. So we can see that this is an open circle. So that means it can equal 4. These are numbers that are less than 4. So we can say x is less than, but it can also equal 4. So there's our inequality. And if we were to name 3 solutions, well, there's an infinite number of solutions. All we need to do is name 3. Well, we can say 3. We can also say 0. We can also say -2. Any number that's to the left of 4 would also be a solution to this inequality. For this example, again, we are at 4, but now there's an open circle at 4, and we want numbers that are to the right of 4 or larger than 4. So this would be x is greater than, but not equal to, 4. And 3 examples of solutions would be 5, 7, and 103. Any number greater than 4 will make this inequality true. In this example, we have what's called a compound inequality. This is 2 inequalities at the same time. Here is the first one. We have x is greater than 2. But we also have this inequality that says x is less than 7. So when we see a compound inequality, this one is telling us it's all numbers in between 2 and 7. X is larger than 2, but at the same time x is smaller than 7. Putting this on the number line, let's say this is 2, this is 3, 4, 5, 6, 7, this is 8, and this will be 1. Our first boundary here can equal 2, so that's an open circle. Can equal 7, so that's an open circle. And what we want is we want the numbers that are greater than 2 and at the same time less than 7. This red region in between 2 and 7, that is our solution set for this compound inequality. This one, it can equal a -4, and we want all numbers that are greater than -4. At the same time, we want the numbers to be less than -1. So let's visualize that on the number line. Call this -4. This will be -3, -2, -1. Here is 0, and this would be -5. Now in this case it can equal -4, so that's a solid circle, but it cannot equal -1, so that's an open circle. And again, we want numbers that are greater than, larger than -4, and at the same time less than -1. So these numbers in between are the solution set. So an example of a solution would be -2. -2 is greater than or equal to -4, and at the same time -2 is less than -1. So here's an example of working backwards. We're given a graph. We want to write the inequality, and then they also want us to find 3 solutions. So here's 0, 1, 2. Clearly this is 2, and this looks like a half in between 0 and 1. Now it can equal a half, but it does not equal 2. We want to put x in the middle. X is the number that represents any of these numbers in here. So x is greater than a half. That's the same thing as saying 1/2 is less than x. But at the same time, x is less than 2. And it can equal a half, so we need to put an equal to here. So these are all the numbers that are greater than or equal to a half, and at the same time less than 2. 3 solutions would be, since it can equal a half is 1. We can also say 1. We can also say 1.5, or 1.6, or 1.99. Any of these will make this inequality true. Thanks for watching.